Hello and welcome to Thermo II. This is our first lecture in a series of asynchronous lectures, and we're going to be covering some of the very basic material that you should have seen in Thermo I, starting with basic definitions, some simple thermodynamic model that we'll be using a lot, symbols, etc. It's a full lecture's worth of notes that I've compressed in 15 minutes, so I'm going to be writing fast. Definitions. Let's start with a thermodynamic system. Thermodynamic system is simply the matter, the mass itself that we're doing our thermodynamic analysis on. So specifically, I'll be talking about the air or the steam in a Rankine cycle that we're doing the analysis on. Some book refer to this as the working substance. I'm going to call it the system. Okay, so it doesn't include piston and the material around it, which is going to be the surroundings. The surrounding is what's around the system, so what contains the mass that we're going to do the analysis on. So again, the piston would be an example of the surroundings, the cylinder walls would be another part of the surrounding, and of course everything outside of that. So those are examples of surroundings. The system is surrounded by the surroundings. Now, what are the thermodynamic properties that we are looking at when we are doing this analysis of the system and its surroundings, right? So what are the properties themselves? A property is simply any observable characteristic of that system. So we're going to be thinking about quantities like the mass, the temperature, the volume, but it can also be other less obvious observable characteristic, like color would be a property, although not one that we talk about a lot. There's two general classes of properties. Some are extensive properties, and those are the ones that are going to be depending on the mass itself that we're analyzing. So you double the mass, you double the value of that extensive property. So mass itself, therefore, would be an extensive property. The volume would be another one like that. The energy, the entropy, etc. There's plenty of them. As opposed to intensive properties, which are those that don't depend on how much material you're doing the analysis on. So all the specific properties fall into that role, as well as temperature and density. It doesn't matter how much mass you've got, the density, if the thing is homogeneous, will be the same. The state is going to be the value of all these properties. Okay, so record what they all are, take a snapshot in time of what all those properties are. That's the state at any given time. An example of that is the standard temperature and pressure of the atmosphere. That's a state that is often a starting state for all kinds of different problems we'll be doing. And the International Standard Association, International Standard Atmosphere and International Civil Aviation Organization define SDP as the temperature of 15 degrees Celsius and a pressure of 1 atmosphere at 0 humidity. A specific type of system is going to be a type of system that's fully defined, where all its properties are fully defined by only two other properties, and we call that a simple thermodynamic system. We'll be using a lot of simple thermodynamic systems in our analyses in this course. Air is a good one. The perfect gases are all, or noble gases are examples of simple thermodynamic systems, and we're going to be talking about many other ones. I want to distinguish the state of the system from the phase of the system. The phase of the system is not the same as the state. The phase is whether or not the substance is a solid, a gas, or a liquid. Don't confuse that with the state. We're also going to need to agree on what a thermodynamic process is. Thermodynamic process is going to be the path that's taking as we go from one state to another. So different processes can get you to the same state, but the effect on the system might not be the same, so it's important to know what we mean by that. An example of that is the compression of a gas in a cylinder. What's a cycle then? Cycle, and here I'm sketching a nice little, just for you to visualize it, I'm a picture of a cylinder being compressed, where the piston's compressing the gas. A cycle is going to be a series of these processes that's going to return the system to its original state. So I start at some point, call it state 1. I do a bunch of things on my system, the gas, for example, or the steam in the case of a Rankine cycle, a power cycle like the Rankine cycle, and I come back to exactly where I was. That's a cycle. Let's talk about a specific model that we are going to be using in this course, the perfect gas model. Perfect gas is the type of simple thermodynamic system, so two properties are going to be fully defining it. And it's a model that I like a lot because it's used in a lot of systems that we're going to be using. Some books refer to it as a calorically perfect gas. I'm simply going to call it perfect gas. It's great for modeling gases like air, combustion products and engines, etc., especially when the temperature doesn't change too much. We're going to stretch that limit a little bit as we use it, but in general, that's the rule, and you're going to see why. A perfect gas is simply a gas that satisfies two main conditions. First is that it satisfies the ideal gas law, can be modeled with the ideal gas law, or IGL, which you'll recall from previous classes and even from high school. Form of the ideal gas law is PV is equal to nRT, where P is the absolute pressure, right, from a zero datum, not a gauge pressure. V is the volume, meters cube or feet cube. N is the number of moles of the gas that we're dealing with. R sub U is the universal gas constant, which has a value of 8.314 joules per gram mole Kelvin, or 8,314 joules per k mole Kelvin. And T is again the absolute temperature in Kelvin or Rankine, not in Celsius or Fahrenheit. Okay, let's remember that. The ideal gas law must hold for the gas that we're going to be modeled as a perfect gas. And we're not going to use it in this chemistry-based model that I wrote there. We're going to change it around a little bit. We're going to introduce a couple of things here to make our life a little easier. So first, define a capital M as the molecular mass of the gas in question, which is simply going to be the mass of the gas divided by the number of moles of the gas that we have. And define R with no subscript, or the subscript of the name of the gas, the specific gas that we're interested in, as the specific gas constant, and define that as the universal gas constant above divided by the mass, molar mass of the gas. And then let's substitute that back into our equation for the ideal gas law here with a little manipulation, multiplying and dividing by the molecular mass. And we quickly get to a much nicer form for the ideal gas law, which is that P is equal to the density times the specific gas constant times the absolute temperature. That's the form we're going to be using in that class. Make this your own. It's an important model. But it's not all. The second requirement for a gas to be perfect is that the specific heats, namely the specific heat at constant pressure and the specific heat at constant volume, which I'm defining for you here, must both be constant. Okay? So for those two things to be constant, it necessarily also means that the ratio of specific heats, which is usually denoted with the Greek letter gamma, and is equal to the specific heat at constant pressure divided by the specific heat at constant volume, a number greater than 1, it must also be constant. And that turns out to be a rather useful thing. So for perfect gas, a bunch of results come out of this, and while they can be proven from first principle, I'm simply stating them for you here. We'll come and revisit this at a later time, but remember that for the time being, that the specific gas constant can be found by the difference of Cp minus Cv, and so that's an important result, right? So you don't need to know the molecular mass of the gas. You can just calculate it this way as well. And also, in the specific case of an isentropic process, a process that takes us from state 1 to state 2, by following a rule, PV to the gamma is constant. Again, we're going to show that that's consistent with the entropy of the process not changing through the process, where V is the specific volume defined as the reciprocal of density. Then PV to the gamma is constant. And when that's the case, it makes for a much simplified analysis of what's going on throughout that process. For example, how the pressure at every point is related to temperature at every point and to the density at every point. It's very, very helpful. For example, the compression stroke in an engine or the expansion stroke in an engine are two examples where we're often going to be using that. All right, a little look ahead since we're gone this far on the perfect gas and some of the things we can do with it. We can define the speed of sound using perfect gas model. The speed of sound is defined simply as the distance that's traveled by a sound wave per unit time. And of course, that can vary with time. And we're going to find that that depends primarily on the temperature, the local temperature of the gas at that point. Again, gamma is constant and R is the specific gas constant. Finally, once you know the speed of sound, you can figure out the Mach number, another super neat thing that we can do with perfect gases, among other things. All right, let's jump into the symbols and units that we're going to be using in Thermo 2 from Thermo 1. First, note that I'm using square brackets here to denote the units of. Let's talk a little bit about energy. Energy is a property when we're just calling it energy, whereas heat and work, which represent transfers of energy, are not in and of themselves energy. They're transfers of energy, so they're not properties of the system. They're not an observable characteristic of the system. They happen in a transient way, which you can measure them, and they have the same unit as energy. Okay, so they're a form of energy, or energy in transit, if you will. E, the capital letter E, represents the total stored energy of the system, and the rate of change of that total stored energy represents the rate of energy transfer, the rate at which that energy is transferred. So it's the rate of change of work energy and heat energy, if you will, with respect to time. Now, what is energy as a property? There's three important forms of energy in a thermodynamic systems that we're going to be using in this course. The first one is the thermal or internal energy, denoted by the letter U. That is, that is a measure of the thermal content of a system, which is itself a measure of the molecular activity that's taking place in our system. So it's intimately related to the temperature of the system, thermal energy, the temperature of the system. And as I'm writing here, U with an upside down caret on top is the intensive thermal or internal energy of the system. Now, the thermal energy and all the energies that we're going to list here are all independent from one another. The other one that's another important form of energy of a system is the kinetic energy of the system, which is defined as half mv squared, and the potential energy of the system, which is the energy due to the relative position of the system above a given datum, mgh. Both of those you're very familiar with from your previous work in physics, most likely, and Thermo 1 as well. We're primarily going to be interested in thermal energy in this course, but the stored energy, capital E, is the sum of all these different energies, and we're going to judiciously decide what matters as we analyze various types of systems as we move through the course. Okay. Now, work, again, it's a form of mechanical energy transfer, and it's therefore considered one of the most useful form of the use of energy, if you will, because we're getting something mechanically useful right off the bat when we're looking at work itself. It's defined as the force times the distance along which the force is applied. And mathematically, you can look at it as the inner product of the force vector times the position vector when it's applied to a system. Heat is simply thermal energy in transit from one place within the system to another, or between the system and the surrounding. But since it can go from the system to the surrounding, and similarly the surrounding can do work or on the system, or the system can do work on the surrounding, we need to come up with a sign convention for both work and heat. And in thermodynamics, the system convention for work is that the work is positive if that energy is being transferred from the system to the surrounding. So the expansion stroke in a cylinder, in an engine, would be an example of positive work, because as the cylinder expands, as the piston expands, it's pushing on the surrounding, and therefore moving in that direction, doing work onto it. In the case of heat, the transfer is going to be positive if heat is being added from the surroundings to the system. And negative if it's the other way around, of course. And voila, you've got it. It's your basic review of some of the very basic concepts from Thermo I, but we need to have a common basis of terminology before we can move forward into more important stuff. Hope you've enjoyed it. Take care. Talk to you later.